Hey guys, in this video, I am going to discuss about a very famous problem that is low level design of rate limiter. We'll first understand what rate limiter does. I can say in network system, rate limiter is used to control the number of traffic that is sent by a client or a service. In simple terms, in HTTP world, rate limiter is going to limit the number of client requests allowed to be sent over a particular period or a specific period. So you might ask me a question, why are we going to block the access calls? So suppose you think about Twitter or Google. So Twitter has 300 requests, tweets. In 3 hours, they set a rate limit. So if you, the moment in 3 hours, you hit the 301th request or tweet in 3 hours, you are going to be rate limited. They are going to block the access calls. So why are we doing this? You can say preventions of the denial of service attack. What is this? Suppose you write a script for your API and your API is going to be every 1 second you are going to hit your API request, and what you are going to see that it is connecting to your database or something, so it is calling a service. So it might be a risk, right? Suppose you don't need that much of TPS or that much of TPM. That we are going to discuss here, that why are we doing this. So I always think in an interview that whenever this question is going to be asked in any designing problem, so it's a very vague question, designing a rate limiter. We don't know the scope of the interview and we don't know the scope of the problem. So that's where we are going to see why want to understand the algorithms of rate limiting before jumping onto the the classes or the methods. That's not the right way. So we'll see here that what are going to be the algorithms of rate limiter. Then only we can discuss about the problem or a solution. So strategy design pattern. This is also we are going to discuss over here because strategy design pattern is a very famous problem. But you will see how we are going to implement this in our rate limiter problem. So we'll see that. Let's try to understand the problem and establish the design scope from there. As an interviewee, my first question of rate limiter would be, what kind of rate limiter are we going to design? Is it a client side rate limiter or a server side? And generally speaking, client side rate limiter is something which is very unreliable because you don't have a control over the client side implementation. It might be possible that client is forged by a malicious attack. So it is very better designed to implement the server side rate limiter. So here also our interviewer wants us to design focus on the server side API rate limiter, and we are going to keep it simple because any low level design interview, they don't expect a compilable code. They expect that our thought process. So should the throttling be based on the IP or user ID? So we'll keep it simple and we'll just simply say that, hey, this is Tofik and this is the user ID. So we are going to just implement that, and which kind of algorithm we should be implementing, that we are going to discuss in the further slides. And also I will talk about the disadvantages. It is not, there is no hard and fast rule of implementing one algorithm. There are many and accurate also. So this is something we've seen. And do all the users share the same rate limit? So as we are going to keep it simple, so we will keep that, okay, 100 TPM we are going to support for all the use cases, and we'll share the same. Let's not make it complicated. And what should happen when a user exceeds the limit? This is very important because obviously when a consumer or a client or a customer is going to get rate limited, they have to know that, okay, our TPM exceeded, so they will try to raise a new use case. So we'll have to say that, okay, you are, through a status code we can say that 429 too many requests and your limit has been throttled. So we can say different messages, 403 forbidden, so something we can do this. But we have to do this. And also the main thing, that concurrency. See, this rate safety is very important because you might have multiple consumers, and it's very important that we track of each and every request with a proper timestamp and thread safety. That is very important. So we got our functional requirements, that is we are going to support on per user basis, and also we are enforcing 100 TPM, and we are going to say a clear message that, okay, 100, that 429 too many requests, your requests are throttling limited. So, and non-functional requirements, the first thing that we are going to take care of thread safety because we are going to handle the race conditions. That is very important. And one more thing, I have always experienced this. So a rate limiter should always be low latency. Suppose my API, whatever I have written the code for it, so it takes 100 milliseconds, and your rate limiter, because of the tracking and everything, it is taking 50 milliseconds. So it's not feasible. My SLA is 100, so I have the agreement that my API should serve within 100 milliseconds, and my rate limiter, if that takes to calculate is 150 milliseconds, that gives me. So there is no point of it, right? So it has to be low latency API, low latency. And modular design, extensible. We are going to implement these strategies and maintainable code base, and if it's efficient performance that we have discussed. Token bucket algorithm, it's a very simple to implement and also famous, widely used by many internet companies. So we are going to implement in this video. And token bucket is nothing but a container that has a predefined capacity. So tokens are put into the bucket at the preset rates periodically. So as you can see that we have 4 tokens available and one request that passes. So one token is consumed. And in the second slide, we are seeing that 3 tokens remaining. So three quick requests are accepted as well. Now the buckets are empty. So requests are going to be rejected or rate limited at the 1.020 milliseconds, right? So we can see that after 1 second, the refill rate is again interval that bucket returns to its full capacity. So what we have seen that it has a two parameters, that is bucket size, the maximum number of tokens a bucket can hold, and number of tokens added every time interval. So it's a very memory efficient solution, but also I can say that since we have a two parameters like bucket size and a refill rate, so it might be difficult to tune them properly. Now comes the leaking bucket algorithm. It is similar to the token bucket algorithm that we discussed, except the requests are processed at a fixed rate. Generally, leaking bucket algorithm is implemented using a first in, first out queue, and the algorithm works in a way whenever a request will arrive, the system will check if the bucket is not full, the request will be added to the queue, otherwise the request will be dropped, and the request will be pulled from the queue basically, and it will be processed at a regular intervals. And here also we'll be having two parameters, that is bucket size and outflow rate. And what I can say, the challenge here in leaking bucket algorithm, since it's a fixed outflow rate use case, whenever a burst of traffic that comes with a old requests, so if this old request will not be processed in this particular time, the other new request will be basically rate limited. So that is one of the challenge I have seen in leaking bucket algorithm. Fixed window counter is one of the simplest approach, as the time window divides into fixed slots, for example 0 to 60 seconds. We count the request in the current window, and as the start of the new window, the count will be reset to 0. And I see the problem here only is the start at the edge of the traffic window, the burst of the request can exceed the rate. So here the limit is 3 per window. So this is a fixed window counter, as you are seeing that these requests are rate limited in this scenario. Sliding window log, this is one of the most accurate approach. Here we will basically store all the timestamps in that particular window, and whenever a new request comes in, we will basically discard all the existing timestamps of the older windows, and we will count the remaining ones. Basically, these timestamps are stored in the cache sorted set of redis, you can say. So as you can see that this allow two requests per minute, so 2 TPM. So first request, you can see that this got passed in that particular time window, and in the second request there, as the allowed timestamps is two requests, so this is also going to get passed. And in the third request, the third one will get basically rejected because it is in the same window. But as you can see that whenever this new request came, that is 1.0140, it passed because of the new window, and it basically deleted all the timestamps. I see in the sliding window approach as it is one of the most accurate approach, but the problem here is it can be a very memory intensive, so it stores even the rejected timestamps as well in the memory. So that is one of the challenge. It will not sure if it is going to be the most optimal solution. Sliding window counter, it is one of the hybrid approach combining fixed window counter and the sliding window log. So let's assume that the rate limiter allowed request is 7 requests per minute, and the previous minute of 5, and in the current minute it is 3. So the algorithm says that the current window plus the previous window, so that means 3 plus 5 into the overall percentage of the rolling window into the previous window. So that means 0.7%. So you can estimate it's as 6.5. So that is rounded up to 6. So the benefit of this algorithm is that it spikes out the rate of the whenever spike of the traffic, it is based on the average rate of the previous window. And the disadvantage I see over here is it is an approximation of that previous window is evenly distributed. So that might not be correct at all the cases. So that is what sliding window counter is. Now we know four algorithms, right? So do you think that these four algorithms we are going to implement, right? So how exactly we should implement? Because see, these four algorithms we learned using, it has all four has some different behaviors, right? So if I write a class rate limiter, a single class, and if I say that, okay, we are going to allow requests based on the user ID that we discussed and an algorithm type that we pass it as a parameter. So today I'm going to write fixed window, we know the token bucket, and we know that there are other sliding window log and sliding window counter, and also leaky bucket. So tomorrow maybe you or anyone can invent another algorithm, and let's say that this rate limiter is in production, you are serving this, and you are choosing one of the algorithm. So do you think that are we going to follow the solid, because suppose today you deployed this application and it is serving properly in the production, but tomorrow let's say the team says that, okay, let's switch to a different algorithm, it should be a hybrid of all of this, suppose, or something. So you will be afraid that, okay, I have to, this class is going to be cluttered so much, and we are going to break the single responsibility principle definitely, and open close principle, because if I change every day, if I modify this class every day, this, it might be possible that in next 10 years this class can grow so much that we cannot maintain this, right? So we'll be seeing that how we are going to use strategy design pattern over here, because see, if else, where you are seeing, right? So whenever you see a lot of if else or switch cases, you think about a behavior driven design, that okay, based on a design we are going to implement, or behavior is going to be changed, right? So we quickly start designing our core classes, and let's see. So enums, we will not be using any enums as of now, I don't see. So now let's see what are the data classes we need. can I say we are going to implement the fixed window strategy? So can I say user request info? This this will be the private static inner class of the fixed window strategy, right? So it will the data holder for the fixed window strategy for a specific user. So can I say I need the window start time because in the uh, fixed window strategy we are tracking based on a time, right? So and since we will be tracking, we need to count, right? So we need a request count info, right? So for a specific user will be requiring this. Now you might ask me question that why we decided for a private static inner class. I can say that okay, that this fixed window strategy, we can this model, can this user request info is valid without this fixed window strategy? No, right? Because fixed window strategy has a map of the user request info it will have. So any other algorithm does not work in this way that we discussed, right? So it is a composition relationship, right? So composition relationship means it's a strong bonding. So without this fixed window strategy, user request info will not exist. So this is that's why we'll be implementing as a now token bucket. So we'll be also implementing the token bucket strategy. So this is also a private static inner class, and I can say it will model the model the user specific details. That is I can say we need capacity, right? So we need to know the maximum capacity and the current token that we have, right? So this is what it says, right? So we have a bucket size, that maximum number of tokens that a bucket can hold, and a refill rate. So I can say that current token, and I can say the refill rate because we need to have a refill rate per second, let's say. So per second, and so I need to also know the elapsed time so that I decide that if the refill will happen or not now. So I need the last refill timestamp. So this is what we require, last refill timestamp. Now, can I have the all the core classes now? Since both these token bucket and request info are, you can say, it's the composition relationship for the specific inner class of token bucket strategy. So let's have the core classes now, since we got the idea that what will be our data classes. And I can say that I will have a rate limiting strategy. This will be interface, and it will have a abstract method. Abstract method. Basically, it will define the contract to implement this both fixed window strategy and also token bucket strategy. So abstract method allow request. I can say allow request, and it will have, so we'll be implementing this, and it will be a boolean, so that we'll be telling that whether it is true or false based on our token bucket strategy and a fixed window strategy. And now can I say that I will have a limiting service, right? So rate limiting service will be a singleton, class that will be implemented. So I can say that it will be primary, okay, it will be primary entry point of the client. With that being said, as discussed, we will be implementing this rate limiting strategy now. So I will have a return type of boolean allow request string of user ID. Sorry, string of user ID. And why this is a boolean? Because the user ID either will be based on true or false. It will be allowed or rejected. So let me just quickly create the fixed window strategy now. So this interface, why it is we have implemented, because this will be okay, we already have a class. So yeah, so this will help in loose coupling. So and now we are going to just implement this rate limiting strategy, and we are going to get an error because we need to implement the allow request method that defines a contract, right? So I'll, yeah, so first private final in, I can say max request. This will be my max request in a window, right? So similarly, we'll be having a final long window size in millis. Why millis? Because milliseconds, the system's current time will be getting in the milliseconds. So we'll be also having, without confusion and calculation, simplicity, we'll be keeping window size in milliseconds. And I can have a map, right? So I can have map of basically string, that is the user ID, and can I say user request info that we previously discussed, right? So this will be my inner class. So I can just simply do one, okay, will be coming that now user request map, right? So new concurrent hash map I'll be keeping because we need the thread safety, right? So we need to properly calculate each and every request every time. So, and what I can do is I can just simply keep private static class user request info, yeah, right? So let's just simply implement this. I can have a long current time that we discussed. Current time equals to system dot current millis, right? We got this. And now what I need is user request map dot put if absent. Will be keeping this method because user ID comma new user request info current time, right? Why? Because whenever a new user comes in, so we'll be just saying that this is my, we'll be creating a constructor long, right? And I can say this is a start time, right? So this is we got, and I can just say that long window start, right? Window start, window is smaller, window start, right? And similarly it will be a atomic operations, right? We'll be calculating each and every request. So the request count, we discussed this, right? So we'll be keeping the request count and we'll be calculating correctly. So let me just have the constructors for this, right? We got our constructors and we'll be object creating the objects with this, right? So I will be simply saying window size in seconds, and whenever we are going to enter, we will be entering in seconds. So we'll be converting into milliseconds, right? Because we need the calculations. So what I can I say that we need basically now we need to get, right? So user request map dot get, right? Get the user ID, and I can keep it inside the user request info equals to user request map and synchronized. So I'll be using the synchronized, where is it? Okay, okay, we'll be keeping that synchronized with code request info. Yeah. So let's just do one thing. I can say if, so why synchronize? Basically because this request info will be logging based on the user ID, not the entire map, right? Not the entire user request info. So can I say the current time we know the current time, right? Current time minus the request info dot uh, I can say window start equals to window size in milliseconds. This is what we got, right? So what I can do is window size milliseconds, right? So now what I should be doing? I should be, so let's see. This is elapsed time, right? So elapsed time greater than equals to the window size in milliseconds. That means suppose my elapsed time is 12,000 milliseconds. That is greater than the thousand. Let's suppose thousand. So what I will be doing? I'll be resetting, right? I'll be resetting. This will be a method on the current time. So what I can do is I will come over here. I will say this will just constructor we need equals to start time, and similarly we need this dot request count equals to new atomic integer of 0, right? So whenever suppose a new window starts, the as soon as the request starts coming, we will then only start, right, incrementing the atomic integer. So we'll be starting with 0, and let's just have a method called void reset, right? So what I can have on this reset is basically what I can keep is long new start. So I'll be having a new start. So what I can keep this dot window start equals to new start, right? So this will be my new start, and this dot request count dot set, I'll be setting it to 0, right? So we got our reset. Similarly, we have one final job, that is request info dot request count dot get. I hope you're not missing this. So max request, right? So let's suppose our current request count is 3, and in that particular window, and that, right? So that is, let's say, 5, right? So 3 less than 5. So what does that mean? So can I say that request info dot request count dot increment get? So we'll be since we are doing atomic operation, right? So and we'll be returning true, right? So that means my request is allowed, and I'll be returning false. So is this I hope this is a simple application, simple strategy we implemented, and I hope we understood what we are doing into it. Thank you. Similarly, now let's create the token bucket strategy as well. Let's implement this abstract method, and we'll be quickly having the two parameters that we discussed, that is capacity, right? And what's the another one? That is final int, the refill rate, right? So refill rate per second. That's how the algorithm works, right? So I need to have the map of user ID, map of user ID string, right? So string of token bucket, I can say. So this is the model we discussed, right? The composition relationship just now we discussed. So new concurrent hash map, I say, and I just define the getter constructors, right? So this token bucket is the model, right? So let me have this private static class token bucket inner class, right? And let's just implement our own logic, right? Current time equals to system dot current time in milliseconds, and we need the map of put if it's absent the user ID. So whenever a new user ID gets created, we say new token bucket. We needing the capacity, what's read rate, refill rate per second, two parameters, and the current value. So current time, right? Current time, and let's create the constructors. I hope you understand this. And current time, let's for say for better readability millis, right? So we can also do something like the compute if absent, if you know the method. Right now I'm just fetching the using this. So token bucket is equals to token bucket map of get of the user ID. So we are fetching the user ID, right? So you can do the compute if absent also instead of two lines. And I say synchronized token bucket, right? Token bucket, and I can say token bucket dot refill, right? So token bucket dot refill, right? So why this refill is needed? Because before allowing or rejecting, you need to first refill the request, right? Tokens. So we'll quickly be implementing this tokens, I can say, and final int refill rate per second, and also I'll be defining the capacity, right? Max capacity. So I can say capacity like this, and I say I need a long of the last timestamp, right? So the last refill timestamp, I can say. So stamp, and let's initialize with this object presence. So this dot tokens equals to the, I can say the capacity, right? So whenever a new user is added to the map, we give them suppose five, right? So five is our tokens. So we'll be giving them that, and this dot tokens, this dot capacity, right? So maximum capacity of the bucket, and I can say this dot refill rate per second. Let's say this is one, and this dot last refill timestamp equals to the current timestamp. So basically, whenever a new user gets added, we'll start with the current timestamp. That is the last refill timestamp. Now let's define the method, right? Refill and long of current. Skip this, sorry, and current time, right? So what can I say? I can say the long elapsed time, right? How much time has been passed to refill, right? So we'll be checking this. So I can say the current time minus last refill timestamp, and you will be seeing what I'm doing. So elapsed seconds, right? So why do we need this? So elapsed time by 1000. So that means I'm rounding it to a second, right? So why I need this? Because you will see that elapsed time greater than zero. That means a refill rate per second. That means let's say one, right? So whenever we will refill, when we will refill, because after 1 second we'll be refilling, right? Let's say one, so it has to be greater than zero, right? So I can say that int tokens to add. So tokens to add equals to, I can say elapsed seconds into refill rate per second, right? Now why I'm getting the error? Because I need to typecast it to, because it's long, right? So we need to typecast it to int, and I can say tokens equals to, can I say math dot min of the capacity? What is the capacity? Let's say five, right? And what we got? Let's suppose elapsed seconds is three, and our refill rate per second is two, so or one. So three into two, let's say six, right? And this is my capacity is only five, right? So I need to get this token plus tokens dot add, right? So how we'll get that? We'll get the minimum capacity, right? So even though it is seven or six, whatever, more than five, it will be five. So that's what we need, right? And I can say last refill timestamp. Last, I need to update this, right? So I can say last refill timestamp equals to elapsed seconds into 1000, right? So again we got in the milliseconds. Now the last thing we need is if token bucket dot tokens greater than zero. If that is zero, what we will say? Token bucket dot tokens minus minus, right? And what will happen? That means return true, right? So requests are allowed. Else what will happen? Return false. So this is it. I hope you understood this. This is fairly simple, I understand, I believe, right? Let's now quickly implement the main service layer, which is rate limiting strategy. So what we need to maintain over here is, as discussed previously, it should be a singleton design pattern we will be implementing, right? Why? Because we need a one shared service object. And the second thing I can say is, first let me implement this and instance, I can say. So why static? Because this variable belongs to the class itself, not to any object, right? So, and I can say the private rate limiting strategy. So why? Because the rate limiting strategy, the rate limiting service should depend on abstraction, not particular concrete implementations like fixed window strategy or anything else. So this would be another job, and I need to have rate limiting service private constructor. So what we are ensuring one single object, right? So and so no new service can do this, like a new rate limiting service like this, right? So and what I need to expose one public get instance, right? So what I can do is insert static and synchronize, so this is thread safe, right? And so rate limiting service, sorry, where I am, rate limiting service and get instance, right? So basically over here what we need to do is first we say that if instance equals to null, this is very important, right? So if null, then only we can do is instance equals to the new rate limiting service, right? So basically we are doing lazy initialization, right? And what I can do is I'll be returning that instance, right? So this is done. Now can I say I will be setting the rate limiting strategy now? So I can say public void set rate limiting strategy, and rate limiting strategy, this dot rate limiting strategy equals to, I can say objects dot require non-null, because if suppose we are handling the null conditions, right? So if suppose someone tries to set the rate limiting strategy as null, so they should not be able to do that. So we need to say throw a proper exception, right? So should not be null, they will get an exception and will be get rid of the null pointer exception basically. And now I can say yeah, so this is done. So now I can say public boolean allow request string of user id, right? So and I'll be just handling the null condition first. If rate limiting strategy equals to null, then I'll be throw new illegal state exception, right? I can throw, so I will be saying rate limiting strategy is not configured, right? So this is done. Now let's just return the rate limiting strategy dot allow request user id, right? So this is done. So this is the magic happening over here. So we're not telling any existing fixed window strategy or something. It's completely configuration driven. That's where the beauty lies of the strategy design pattern, right? So public, I can say public void handle request, right? We should be handling the request, we should be printing, right? So I can say string user id, and I will be basically saying that if allow request of user ID is there, then I will be printing, right? So what I'll be printing, request of the user ID is allowed, right? Else I'll be saying that simply printing this thing. Let's copy paste. So I can set this, and request of the user ID is rate limited, rate limited, right? Clear message. So yeah, rate limited. This should be our implementation for this rate limiting service. Let's quickly have the demo now, since we have the concrete implementations, right? So let's quickly implement the topic as user ID and fixed fixed window demo, right? This way, and I can have the method ready, fixed window demo of user ID, and also similarly we'll be copy pasting this, right? So token bucket, right? And also I can have this token bucket demo of user ID. Let's have this implementations. Okay, we'll be implementing one by one. Sorry. Yep. So int capacity. Can I say if I rate? I can int refill rate is 1, and I can say rate limiting strategy token bucket strategy equals to new token bucket strategy. This is the magic, right, of strategy design pattern, right? So one side is my abstraction, another side the concrete implementation. So limiting service equals to rate limiting service dot get instance one singleton object, right? So I can have this token bucket strategy, right? Simple. So executor service, I need this. And why? Because I need to create a thread pool, let's say with 2, right? So computers dot new fixed thread pool, that is let's say 2, right? And what I need, so I just say try first. I think I need to have simulate the request, right? So int I equals to 0 to 0 and less than 10 I plus plus, right? And there I say executor service dot submit, and I can simply do like this lambda, right? And what I can say is service dot handle request of user ID. Basically it will say if that is rejected or allowed, right? So this is like a runnable interface. It comes from a runnable interface run method, so you can check that out. We can also implement like this. So for the time being we'll do this, and Yeah, so what I need is, I can say thread dot sleep. We'll block the threads for, I can say, 300 seconds, and we need to catch the interrupted exception E. I can say thread dot current thread dot interrupt for the best practices, and our implementation is ready. And I can say execute a service dot shutdown, right? So what I'm saying by this is, let's just finish the current task, then only pick something else. So, and now let's, can I say int max requests is 5 and int window in seconds, so in seconds, and it's equals to 10, and I will just copy paste everything now. Here will this be good. Yeah, so here I'll be changing to fixed window strategy equals to fixed window strategy and max requests and window in seconds, right? And what else? So fixed window strategy, I can say thread pool is 3, let's say 3, and let's have something else. I think we are good. Now let's run this demo. I'm pretty excited. Let's see what happens. So request is allowed, checked it. Okay, so we are giving the clear messages each, right? So this is good, right? So let me just come back with the full class diagram. What exactly we had previously. We started with the simple interface, and we have this implemented fixed window strategy, token bucket strategy, and each one having a composite relationship with the user request info, and similarly token bucket and the rate limiter demo is for the demo purpose, right? So I think we are good with this design, I hope. And I just want to say that this video is completely in a way made in a way that you revise quickly. So suppose tomorrow is your interview, and we'll be coming here and just knowing what is happening, we should be understanding in a pretty quick manner, and just last minute revision, that's it.